Hi, it's Kate, and this is the fifth video for week 1 of Math 23B. We're going to take a moment and talk about when functions are Riemann integrable. First, earlier we discussed that to be Riemann integrable, a function has to be bounded, as in it cannot be an unbounded function. It can't have asymptotes, and it also has to have bounded support, as in the interval of integration must be finite. But that's only a necessary condition, that's not a sufficient condition. So one example of a bounded function that is not integrable, that also has bounded support, is this function that equals 1 for rational numbers between 0 and 1, and 0 for irrational numbers between 0 and 1, and we want to integrate it over the closed interval from 0 to 1. So clearly it has bounded support. It also is a bounded function. But note that no matter how finely we slice up this interval, how high of a level of dyadic division we use, no matter how small these dyadic cubes are, you will always be able to find a rational number and an irrational number inside any dyadic cube, no matter how tiny it is. And so what ends up happening is that the upper sum, regardless of the level of dyadic division, will always be 1. The lower sum, regardless of the level of dyadic division, will always be 0. And so as the level of dyadic division goes to infinity, the upper and lower sums fail to converge. The upper sums are always 1, the lower sums are always 0, and so the function itself is not Riemann integrable. Note that there's some good vocabulary that you can use to describe exactly what we're talking about, and that's called the oscillation of a function over a dyadic cube. And the oscillation is the difference between the supremum and the infimum of the function values over that cube. And so in our previous example, when we had the rational numbers achieve a function value of 1 and the irrational numbers achieve a function value of 0, the oscillation within any dyadic cube, which would contain both a rational and an irrational number, would be 1 minus 0, so the oscillation is equal to 1. And so what ends up happening is that when you have something that's not integrable, as in the upper sum and the lower sums do not converge to the same limit as the level of dyadic division goes to infinity, that means that the oscillation does not go to 0. The upper and lower, the difference between the upper and lower sums maintains some finite value. We rewrite this formally here, specifically stating that if you have a uniformly continuous function, the oscillation must approach a limit of 0 as the level of dyadic division gets larger and larger and larger. And so in this particular example up here, our oscillation maintained at 1, regardless of how finely we were slicing that interval. Now we can restate a necessary and sufficient condition for integrability by clarifying the following in this comment that says for all epsilon greater than 0 there exists some capital N such that the combined volume of all dyadic cubes at the level of dyadic division, big N, for which the oscillation exceeds epsilon is less than epsilon. And so that's basically saying that as you make epsilon smaller and smaller and smaller, the number of cubes whose oscillation is larger than that epsilon itself gets smaller and smaller and smaller. That takes some time to think through, but we'll be working with it in class this week. The big takeaway there as you're thinking through all this is to realize that we're taking a magnitude of oscillation and saying that if we have an integrable function, we are certain to find a level of dyadic division, maybe larger cubes, maybe really tiny cubes, but there exists some level of dyadic division where the number of cubes whose oscillation is greater than that magnitude have a collective volume that's less than that magnitude. And so what's interesting is to say we can choose a level of dyadic division sufficiently large to basically make the magnitude of oscillation as small as we'd like. That's what it means when you're dealing with an integrable function. So as we start to explore these ideas, we're going to talk about good cubes and bad cubes. The good cubes are the cubes where the oscillation is less than epsilon. And note that their total contribution to the difference between the upper and lower sums is going to be less than epsilon times the volume of the support of F, because not every single cube is going to be a good cube. Meanwhile, you also have bad cubes, where the oscillation is greater than epsilon. And remember that the bad cubes will be no more total volume than epsilon itself. And of course, the maximum oscillation in a bad cube is going to be no greater than twice the supremum of the absolute value of F. In both of these comments, you might be wondering, why does it matter what the total contribution to the difference between the upper and lower sums is going to be from the good cubes and from the bad cubes. We just want a bound on it so that we can use that in later proofs. And you'll see that come up in later concepts about how much oscillation can you expect, how can you show that the oscillation is going to zero. And so it's important to realize that if you took the function f and you looked at the absolute value of that function, well, the oscillation within a cube, not of the absolute value function, but just the actual oscillation within a cube, is going to be no more than twice the supremum of the absolute value of the function. And we also know that the total volume of these cubes is going to be less than epsilon, so you'll see this concept occur when we're trying to give some upper bound to how much are the bad cubes really contributing, how much are the good cubes contributing. And so we'll be using this in one of our proofs later on. Interesting, we have a couple of examples that we'll be going through in lecture about functions that are discontinuous but integrable. So here's a standard example of a function that is discontinuous at infinitely many points on the interval 0 to 1, yet is nonetheless integrable over that interval. Note that x is equal to p over q in lowest terms, and f of x is equal to 1 over q. It is 0 everywhere else. And so we're going to walk through exactly how this function ends up being integrable. The idea is basically whenever you choose an epsilon greater than 0, there are only going to be finitely many rational numbers for which their actual function value is greater than this epsilon. And then you can choose a level of dyadic division that captures these in small enough cubes so that the total combined volume of the dyadic cubes that have these sort of bad points in them only have very negligible volume. So we'll go over that in depth as an example in class, but it's something to sort of think about as you're starting to experiment with some of these ideas. That's it for week 1. The major points are to determine exactly what is Riemann integrability. Make sure that's clear in your head. What are upper and lower sums? How do they work? What are some applications of integration in multiple dimensions? And a few different properties of integrals. And then finishing off, we're going to be talking about, okay, when you're actually looking at what is enough to say that something is integrable, this is the major takeaway right here. That you're actually able to choose a level of dyadic division where the number of cubes that violate some pre-chosen oscillation is going to be less than epsilon. But I would say those are the main points that you really want for this week as we go into lecture sections and the problem set. If you have any questions at all, please, of course, don't hesitate to email.